Well, hello again. Welcome to our journey into linear algebra. I thought we'd finish off this section on Cayley Hamilton with just a little note on the Fibonacci numbers and to show some nice connections between matrices and Fibonacci numbers. This is not really so much to do with Cayley Hamilton, but I thought I'd just tuck it in here because it's quite a nice little piece of mathematics. So I'm going to start off with this matrix, this fairly harmless looking matrix. And I'm going to start calculating the powers of this, and we'll see it gives us a nice link, a nice connection back with the Fibonacci numbers, and we can get all sorts of interesting facts about the Fibonacci numbers themselves out of studying the powers of this matrix. So, just as a little experimental bit, firstly, we start off with, there's the matrix A. I take the matrix and I square it, so I'll leave you to check that's what you get. When you square it, you get 1, 1, 1, 2. You cube it, so I'm going to take this and multiply it by it again, and I get 1, 2, 2, 3. You can already see some patterns appearing. And a to the fourth, I multiply this one by a again, and I get 2, 3, 3, 5. And now we sort of start to get excited because we could be beginning to see the Fibonacci numbers appearing, and if you would go to the fifth power, you would see a similar pattern. You would see 3, 5, 5, 8 coming here. I'll leave you to check. Now, just recall the Fibonacci numbers are the numbers 0, 1, 1, 2, 3, 5, 8, 13. And so I'm going to call this one A0, this one A1. And then the whole point about the Fibonacci numbers is that every number in the sequence is the sum of the two before it. So an is an minus 1 plus an minus 2 for n bigger equal to 2. And that defines the Fibonacci sequence. Now, it's not a difficult induction, in fact, to prove that our suspicions by looking at the numbers in here do in fact hold. That is, that the nth power of this matrix contains the Fibonacci number. So the nth power has the nth Fibonacci number here, the n minus 1th one here, and the n plus 1th one there. And that's a fairly easy induction to prove. So you simply need to, for the inductive step, you simply look at a to the n times a, and when you multiply it out, you'll see you get the next terms in the sequence, and all is well. So it can be easily shown, in fact, by induction that this is true. Now, immediately we can get some lovely things out of this. So one is tempted to take determinants of both sides. And so I shall give in to temptation and take the determinant of both sides. Now, of course, the determinant of an is just the determinant of a all to the n. And that's the determinant of the matrix 0, 1, 1, 1 all to the n, and that just gives me 0 minus 1 to the n. So the determinant on this side is minus 1 to the n, and the determinant here is a sub n minus 1 times a sub n plus 1 minus a sub n squared. And this is a well-known identity that just falls out. Beautiful, falls out immediately just taking the determinant of this matrix here. So just to enjoy what it says in terms of the sequence, it simply says if you pick two Fibonacci numbers 2 apart, so if you take this one times that one, you get 10, and 10 minus 3 squared is 1. And if you took, say, these ones, you'd get 8 times 3 is 24, minus 25 is minus 1. And so on. So 5 times 13 is 65, minus 64 is plus 1. So it's one of those lovely identities that you may have seen connected with the Fibonacci numbers. Well, you can do more. For example, if I take a to the n times a to the m, then a and a commute, so this is just a to the n plus m. And using our formula up here that we had for a sub n here, then we can write down what this matrix looks like in terms of the Fibonacci numbers. It's a n plus m minus 1, and there's the n plus mth Fibonacci number there and there. I'm only interested in this one, in fact. And on the other hand, if I multiply an times am and multiply it all out, then I'll get something there, something there, something there, and this one is going to be a sub n minus 1 plus a m plus 1. And now I just equate the components, and that tells me a n plus m is given by this formula. So this gives me a way of finding the n plus mth Fibonacci number if I know the nth and the mth one. Another well-known result from theory of Fibonacci numbers, but one that just pops out nicely by the index laws up here and just matrix multiplication. Well, of course, it's nice also to find, we'd like to find a general formula for the Fibonacci numbers, which you've probably seen, and I'm going to do that by diagonalizing. So I'm going to find the eigenvectors and eigenvalues for this matrix A. So I'm going to set A minus lambda I to be 0, and this gives me, there's the characteristic polynomial, and I solve that, and of course out comes these two beautiful numbers, the golden ratio, 1 plus root 5 on 2, and its conjugate 1 minus root 5 on 2, and I'm going to call that alpha and alpha bar. It just makes the arithmetic easier. Now the eigenspace for alpha is going to be the kernel of, so I'm just going to pop that back up into here, and it's actually easier to work with the bottom row here. So I'm going to take 1 minus root 5 on 2 lots of that, and then minus 1 lot of that, and that'll be in the kernel. And that's alpha bar minus 1. And the eigenspace for the alpha bar is just the conjugate of this one. I'll leave you to check, you just get alpha and minus 1. So if I whack these into a P matrix now, then this is alpha bar minus, this is alpha bar minus 1. That's this eigenvector here, and that's the other eigenvector there. And then the diagonal matrix, keeping the same order, will have alpha there and alpha bar there. Now P inverse AP is D, because this is a diagonalizable matrix, and again using our usual trick here, we undress A, we move the P there, the P inverse there, and we take A to the N, and we get P D to the N times P inverse. And D to the N is easy, we just raise the diagonal elements to the power N. There's the P matrix, I guess the P inverse, and I have to divide by the determinant of this one to get the inverse. Now alpha minus alpha bar is 1 on root 5, and I've just multiplied these three matrices out. And I'm really only interested in the first entry, so you get this, then you'll get something, 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 and this is supposed to be equal to a to the power n, and the first entry in a to the power n is the n minus 1th Fibonacci number. So I can say a sub n minus 1 is 1 on root 5. I take an alpha alpha bar out of both of these, so there's an alpha alpha bar, and that leaves me with an alpha bar to the n minus 1 minus alpha to the n minus 1. Now when you multiply alpha times alpha bar, you end up with minus 1. I'll leave you to check that. You get minus 1. So I use that minus, and I'm going to just replace n with n plus 1, so I get the nth Fibonacci number is going to be, and I'll use the minus here to flip these around, so I get alpha to the n minus alpha bar to the n. And plugging back in the alpha and alpha bars, that gives me the standard formula for the nth Fibonacci number. And there it is. By the way, just as a little final note here on this, you can do so much fun with Fibonacci numbers, they're really interesting, but it's nice, you can get a lot of these identities and things out by simply using matrices. But just note here that for large n, 1 minus root 5 on 2 is less than 1. So when you take its nth power, it's very small. So if n is large, the nth Fibonacci number is roughly, not exactly of course, but if you want to get the nth Fibonacci number quickly, you just do this and take the nearest integer. This is for large n, because this term here is very small. So anyway, that was just a little application of matrices to Fibonacci numbers just to round off this section.